In this video, we're going to talk about determinants. Now, if I call A a matrix, here's A. This is a matrix. The determinant is a function that turns this matrix into a number. So we use two vertical lines, kind of like absolute value, to denote the determinant of a matrix. So this is the determinant of A, and that's another way to write it. And the thing to note that this is a number, like 5 or 7 or -3. This number can be positive, negative, fraction, any type of number. So if I were to write a matrix like with square brackets like we usually do, like 1, 2, 3, 4, that's a matrix. And when I want to talk about the determinant of that matrix, instead of the square brackets, I just put two vertical lines like this. So now this is a determinant, and this is equal to a number. Now in this video, we're going to focus on the properties of determinants. And there are three properties that we would like to focus on. The first one says that the determinant of the identity matrix is 1. So here, the determinant of the identity matrix is 1. We have the 2 by 2 identity matrix, and the determinant is 1. And we have a 3 by 3 identity matrix, and the determinant is 1. Any size identity matrix has determinant 1. The next defining property is that if we interchange two rows, then the sign of the determinant changes. So here we are interchanging the first row and the second row, and notice that we're talking about determinant here because we have two vertical lines, so the determinant becomes negative. Okay, so every time there's a row exchange from one step to the next, you have to change the sign of the determinant. That's the second defining property. The third defining property is that the determinant is a linear function of its rows. Now this is, for people that just learned properties of determinants, this might be the more difficult one to understand. And there's two parts to this linearity. Okay? And the other part that we have to take into account is that this linearity needs to be understood as taking one row at a time. So the first part of linearity comes from addition. So here the first row has A plus alpha, B plus beta. The second row CD. When I break this determinant up into a sum of two determinants, I keep one row unchanged. So notice here that the second row is kept unchanged and the addition is coming from the first row. So the first row is being broken up so that A plus alpha and B plus beta, that's the sum that's broken up. That's one part of linearity. The other part of linearity comes from factoring out a scalar from a single row. So I can factor out a scalar from a single row. Here the first row is TATV. I could factor out T, and the determinant basically multiplies that scalar to keep things unchanged. So these are the three defining properties of linearity. Now let's go to look at a specific example. And in this example, we're going to try to figure out the determinant of A, B, C, D, the 2 by 2 matrix. Now remember that we know this from before, that the answer is AD minus BC. Now we know this is the answer, but let's see if we could just use the defining properties to come up with that formula. So now let me use linearity to start. And when you're going to use linearity, the addition version of linearity, you're going to break the determinant up into a sum of two determinants. You have to decide which row is going to change. Every other row is going to stay fixed. I'm going to keep the second row unchanged. And the first row, AB, I'm going to write it as A plus 0, like this. and 0 plus b like this. So that gives me AB, okay? So a plus 0 gives a, and 0 plus b gives b, so that's fine, okay? Let's get rid of these. All right, so that's using linearity, the addition version. Now I'm going to use linearity by factoring out a multiple. And the multiple I'm going to factor out is a from the first row and b from the first row in the second matrix. So if I use linearity again, I'm going to put a times 1, 0, CD plus b times 0, 1, CD. Okay, here we are. So this is using linearity, the addition version in the first step, and the multiplication by a scalar of one row in line 2. Now I'm going to use linearity again, but this time I'm going to keep the first row unchanged. So I'm going to say for the first matrix, I'm just going to focus on this determinant. 1, 0 plus 1, 0. There we are. So that row is not changing. The CD is going to change. So I'm going to put C0 and 0D. And this is coming from the first matrix, okay? And they're both multiplied by A, okay? Because A was the multiplier. Plus, now let's focus on the second one. So if I break up the second one, again, I'm going to keep the first row unchanged. And the second row CD, I'm going to write it as C0 and 0D. And of course, they're both multiplied by B. Okay, so this is the second one breaking up. Okay, and let me use linearity again on the green part. So I'll just copy the blue part. Well, maybe I should use linearity again. Let me factor out C from the second row. So I get AC 1, 0 and 0, 1. Or never mind. 1, 0 again, plus A, here let me factor out D from the second row. So that puts D outside, I get 1, 0, 0, 1. Plus, now let's do the green parts. I'm going to factor out C again from the second row. So I get 0, 1, 1, 0. Plus, I'm going to factor out D from the second row, so BD times 0, 1, 0, 1. So here we are. So we've managed to break up this original determinant into a sum of 4 determinants, right here. Okay? Now, all we have used is linearity, both versions, the addition and the multiplication. Let me remind you of another property. The first defining property, remember, says the determinant of the identity matrix is 1. So if I go back to my example, where is the identity matrix here? Here is the identity matrix. So the determinant of that is 1. So that's going to give AD times 1. Okay, we'll worry about the others in a moment. If I go back here, the second property says interchanging 2 rows changes the sign of the determinant. Now if I focus on this one, this is just like the identity, but 2 rows are interchanged. So for that one, BC is multiplied by, well, what was the determinant of the identity? It was 1, and then I did an interchange, so it becomes -1. Okay, so that takes care of these 2. Now let me look at the other ones. So let me look at this orange one and this one. And for that, we're going to go back and look at, again, the same property, that interchanging 2 rows changes the sign of the determinant. Now, there's an interesting way to look at that when we have a repeated row. Let me jump ahead and talk about the fourth property. If 2 rows are equal, then the determinant is 0. Let's see why. Here in this matrix, I've set it up so that the first and third row are the same. So if I swap them, the determinant needs to change sign. But swapping them doesn't really change anything, right? It's the same exact matrix. So basically, if one number equals the negative of another, and both numbers are the same, the only number that stays the same when you change its sign is 0. So the determinant is 0. Okay? So let me go back and review this. If two rows are equal, then the determinant is 0. So having said that, if I go back to my example, this determinant is 0. And for the same reason, this determinant is 0. And so finally, let's write the final answer. That's 0, that's 0. The final answer is AD minus BC. So these defining properties are so specific that they completely determine the determinant. And of course, in the future, we're going to have formulas to do this quickly. And I will never ask you to do this manually. I'll just say, for the 2 by 2 multiply the diagonal numbers. What is that? That's AD. And then subtract the other diagonal, BC. And that's it. That's how we would typically do it. But I wanted you to understand how these defining properties are used to find the determinant of any matrix. Okay? In the next video, we're going to understand more properties. That is going to make our work a lot faster, a lot easier, and it's going to give us some insight of how in the future we can apply these ideas to systems of equations.